Okay, we're going to jump into lesson 5.1/5.3, which is going to be on linear equations and rate of change. So first, when we're looking at a linear function or a linear equation, we know that it should produce a line when it's graphed, right? That's why it's a linear equation. The largest exponent that we have is 1, and it should have a constant rate of change, which some of us know as the slope. So those are kind of three requirements for a linear function or a linear equation there. And the one I want to focus on for this next part is this constant rate of change, which is one way we can tell if we have a linear function. So scrolling down here, it says use the given information to determine if the scenario or equation represents a linear function. So I'm going to go ahead and input what I have from the graph into my table. So the x values, it looks like they go from 1, 2, 3, 4, and 5. And then my outputs, my y values here, looks like we have 210, 420, 6, 30, 8, 40, and 1050. Okay, and so the key here is to determine if we have a linear function is to determine if we have a constant rate of change. So we can see my outputs are increasing. Looks like we increase by 210 there. We go up by 210, and then we go up another 210, and we go up another 210, and up another 210, all while we're going up by 1 here. So we have a constant rate of change because we continue to increase by 210 each time. So then I know that this is going to be a linear function. So then I'm going to put yes, linear, because we have a constant rate of change. Okay, moving to this next one here, letter B, same deal. We're going to check this out. They've already got the table filled in for me, and it's asking if this is a linear function. So as I check out my outputs here, it looks like we increase by 3, and then by 5, and then by 7, and then by 9. We can see that that's not a constant rate of change. There is a pattern there, right? But we're not increasing at a constant rate of change. It's not the same number over and over and over again. This should sort of remind you of an arithmetic sequence, right, which we looked at previously. So it doesn't generate an arithmetic sequence. It doesn't have a constant rate of change. So this is not going to be a linear function because we don't have the same number over and over and over again. So then I'm just going to put no, not linear. Another way that we might be able to tell this is not linear is I can look at the equation that they use, which is x squared. Remember, if I scroll up here, it says the largest exponent is 1. We can see in this function, our largest exponent is 2, right, because it's being squared. So we would have known right off the bat that this was not linear. Okay, we're going to look at standard form of a linear function. You've probably seen slope-intercept form of linear functions, right? That's the y equals mx plus b that a lot of people are familiar with. If not, we're going to get there in this next section. But for now, we're going to start with standard form. And I want you to notice a couple things about standard form. First, we have x and we have y on the same side of the equal sign, right? Which is a little bit different from slope-intercept form. So they're on the same side. And the other piece that I want to note here is that we're going to try to eliminate all fractions. So I'm going to put no fractions. And so if we can get our equations into standard form to look like this, then we know that they're going to be linear equations, that they're going to be linear functions. So our goal is to get our equations to look like this, and that way we know that they are linear. So scrolling down here, it says determine if the equation is linear, explain your answer. So basically they're asking, can you get it to look like standard form, right? Or does it already look like standard form? So for this problem here, right, we look at it, it says determine if it's linear. Well, we have x and we have y on the same side. We have no fractions, right? And so we can see that our largest exponent here is 1, right? Remember, if there's no exponent, that's like an imaginary 1 there. Okay, so in this case, we don't really have to do any work. It's in standard form already for us, and so we're good to go. So it says explain your answer. Yes, linear, because in standard form. Okay. Let's check out another one here. So looking at letter B now, same idea. X and y are on the same side, right? Our largest exponent is this imaginary 1 that's there. Okay, no fractions, and so we can say yes again that this is linear because it's in standard form. And now let's move down to letter C. Okay, so for this one, we've got x and we've got y, and they're on the same side, right? We've got no fractions, but notice our largest exponent is 2, right? We have an x squared, so then we know that this is not going to be linear. Not linear. And you could add because we have an exponent larger than 1, right? We've got x squared, so that's not going to be linear. And then scrolling down to letter D here, okay, we've got x and y on the same side, right? But we've got this fraction here where x is in the denominator. So once again, remember we said no fractions, and there's no way to fraction bomb this to get x out of the denominator. So then I'm going to put no, not linear. Sometimes there will be cases where we can rearrange things to get rid of fractions, but in this case, no matter what I do, I'll be stuck like this with a fraction here, and that's not going to work. All right, real quick, we're going to kind of review discrete versus continuous. We've talked about this before. It says determine if each function is discrete or continuous, and then graph the function. Sal opens a new video store and pays the film studios $2 for each DVD he buys. Okay, the amount Sal pays is given by this function, f of x equals 2x, where x is the number of DVDs. So x represents the number of DVDs. So if I wanted to, I could label that down below here on the graph, right? These are the DVDs. Okay, and so we can go ahead and graph this using a table if we want. So I'm going to go ahead and create a quick table. I can punch in some values for my domain, 0, 1, 2. Okay. Notice I didn't pick any negative values because x represents DVDs and we couldn't have negative DVDs. All right, so I'm going to punch those in for my equation here into x. So let's see, if I buy 0 DVDs, then it's $0. 1 would cost me $2. 2 would be $4. Okay, and I can continue this going, right? I'm going to stop it there, though. And it wants me to determine if this is discrete or continuous. Remember, that's all about what my independent variable is. In this case, it's DVDs. Can you break DVDs into parts, right? Would you want 1.5 DVDs? Hopefully that's a no. So in that case, it means that this is a discrete graph. And if you're not sure why, right, then you can go back and visit our lesson about discrete and continuous variables. Moving on to letter B, it says Elsa rents a booth in her grandfather's mall to sell ice cream. She pays $1 to her grandfather for each hour of operation. The amount Elsa pays each hour is given by this function, f of x equals x, where x is the number of hours. So we have hours down here. And so for this one, you can make a table again, but this one's pretty straightforward because this is a function, just f of x equals x. So I'm going to do 0, 1, and 2 again, and I punch those in, right? If I plug in 0, I just get 0. If I plug in 1, I just get 1. If I plug in 2, I just get 2. And then onto the graph here. And now we have to decide, okay, well, is our independent variable, in this case the hours, is this discrete or continuous? Well, can you have 1.5 hours? Sure, right? You could get paid for 1.5 hours if you went into work, right, and you did 1.5 hours. Well, then you should get paid partial credit for that. So we can go ahead and connect our points here.